Hi Year 13 and welcome to this video on bases. We're going to compare strong and weak bases, we're going to look at what bases are, and we're going to look at how to calculate the pH of bases as well. So, first of all, what are bases? Well, bases are proton acceptors. That means they accept an H+ whenever they react. So if we look at this example of ammonia, NH3, when it's placed in water, we can see here that the products formed are NH4+ and OH-. So the NH4+ is the NH3 after it has gained an H+ from the water. And the OH- is the water after it's lost an H+ to the NH3. So the water, in this case, is acting as an acid, and the NH3 is acting as a base. And they're formed on the right-hand side here, NH4+ as the conjugate acid of NH3, and OH-, which is the conjugate base of H2O. A quick reminder there that a conjugate acid-base pair should differ by one H+. So if we compare NH3 and NH4+, we can see that the acid form has the extra H+, it's got 4 H's and a positive charge, and the base form does not have the H+, it's only got 3 H's and it's missing the positive charge. So they therefore are a conjugate acid and base pair. Basic solutions should also have a higher concentration of OH- than H3O+. As we can see, OH- ions are produced by the reaction of bases in water, therefore their concentration should be higher. This results in a pH value greater than 7 for basic solutions. Let's now have a look at strong bases. Strong bases completely dissociate when placed into water. Here's an example of one, sodium hydroxide. We can see that with this full arrow, that represents it's completely reacting, and it's forming its two ions, Na+ and OH-. It does this when it's in water. So just note that strong bases are not like strong acids where they react with the water molecules. They are simply completely breaking apart into their ions as they are already ionic compounds. So the ions in this ionic compound are fully separating when being placed into water, resulting in 2 aqueous ions. There are only 4 strong bases. That's how we know when we're dealing with a strong base, from memory, knowing that there's only 4. And those 4 are NaOH, KOH, LiOH, and CaOH2. Sodium hydroxide, potassium hydroxide, lithium hydroxide, and calcium hydroxide. And again, all 4 of those are ionic compounds. They all contain a metal, calcium, lithium, potassium, sodium, and a non-metal or non-metal group, which is hydroxide in each of these cases. So how do we calculate the pH of a strong base? Well, let's take, for example, a 0.1 mole per litre sodium hydroxide solution. We can first of all write an equation showing what it does in water, and that is that it fully dissociates. We know from memory that NaOH is a strong base. We have its concentration, so if I had 0.1 mole of NaOH, it's going to completely break apart to give me 0.1 mole of Na+ and 0.1 mole of OH-. So each one of these particles breaks in half to give one of them and one of them. So I can see from the equation here that I have 0.1 mole of OH- in my solution. So my concentration of hydroxide is 0.1 mole per litre. Now to find pH, I don't want OH-, I need H3O+. So to find H3O+, I need to rearrange an equation. And that equation is this one here, the Kw equation, where Kw equals H3O+ times OH-. Kw is a constant, it's always 1 times 10 to the minus 14. I can rearrange this equation to find the H3O+ from the OH- and Kw. And its rearrangement looks like this. H3O plus equals Kw divided by OH minus. If I now plug in my values, Kw is a constant, it's always 1 times 10 to the minus 14. My OH minus was 0.1 mole per litre. I now have my H3O plus concentration as 1 times 10 to the minus 13 mole per litre. From the H3O plus, I can now calculate the pH. pH equals negative log of H3O plus. I can input my H3O plus value as 1 times 10 to the minus 13, and that will give me my pH, which is 13. This sounds like a very reasonable pH value for a reasonably concentrated solution of a strong base. So it ticks the logic box. Let's now have a look at weak bases. Weak bases only partially dissociate in water. They're going to form an equilibrium, as we can see here from NH3 when it's placed into water. It forms the ammonium ion and hydroxide, and again we're seeing that H plus being transferred from the acid to the base. So NH3 is again acting as a base. If I had 0.1 mole of my NH3 base, I don't know how many mole of NH4 plus I would get, or OH minus, because it's not fully dissociating like the strong bases. So I cannot come up with a concentration of OH minus and go on to work out the pH as simply as I do for a strong base. There's going to be more steps involved. Because I'm dealing with an equilibrium, I can write a K expression, just as I do for my weak acids. This time I'm going to call it Kb, the B standing for base. Kb equals products over reactants. Here are my products over here. So NH4 plus and OH minus over my reactants, NH3 and water. Just like for weak acids, we are going to exclude the water because its concentration is so large that we can assume it to be constant. So therefore my Kb expression equals NH4 plus multiplied by OH minus, and those two divided by the concentration of NH3. We can again compare the Kb values for various weak bases to show how strong each weak base is. So again, here's a table that we'll talk to. I've got two bases, NH3 ammonia and HCO3 minus hydrogen carbonate ion. They've both got Kb values, 1.8 times 10 to the minus 5, 2.27 times 10 to the minus 8. The bigger of those two values is this one, 1.8 times 10 to the minus 5. That indicates that NH3 has an equilibrium that will go further to the product side. Therefore, NH3 is going to be my stronger weak base. It is going to dissociate further into ions than HCO3 minus would. Again, we can see this thing called pKb. Now that's taking our Kb values and turning them into something a little bit more user-friendly, just as pKa does for Ka, or pH does for H3O+. We can convert between Kb and pKb using these two equations. pKb equals the negative log of Kb, and to get back the other way, Kb equals 10 to the power of negative pKb. I can see that my pKb for ammonia is 4.74, and I know that ammonia is the stronger of the two weak bases. Therefore, the lower the pKb, the stronger the weak bases, and the larger the Kb, the stronger the weak bases. So again, a trend that we can use to compare weak bases and determine their relative strength. Another way that I can compare weak bases is to use the Ka values of their conjugate acids. The reason I can use this is because for any conjugate acid-base pair, the following equation is true. Ka, which is the equilibrium constant for a weak acid, multiplied by Kb, which is the equilibrium constant for a weak base, will always equal Kw, which is 1 times 10 to the minus 14. What this equation tells me, however, is that if I have a Ka value for a weak acid that is high, its conjugate base must have a smaller Kb for Kw to remain a constant. As one goes up, the other has to go down to maintain this as a constant. So what that means is, if my weak acid is relatively strong, its conjugate base must be relatively weak so that this can remain a constant. So a stronger weak acid, which is a higher Ka, will have a weaker conjugate base that has a lower Kb. So I can compare weak bases using the Ka values of their conjugate acids. This equation is going to be very helpful for helping us to calculate the pH of weak bases also. So let's work through some calculations here. First exercise, calculate pKb for ammonia, given that the Ka for ammonium, its conjugate acid, is 5.75 times 10 to the minus 10. This is going to be a two-step calculation. First of all, to calculate pKb, I need to start with Kb. To get Kb from Ka, I'm going to have to rearrange the equation Ka times Kb equals Kw. So Kb will equal Kw divided by Ka. That's going to equal 1 times 10 to the minus 14 divided by the Ka, which is 5.75 times 10 to the minus 10. Plug that into your calculator and it should come out with 1.74 times 10 to the minus 5. So there's the Kb for NH3 calculated from the Ka of its conjugate acid. I can't just use any old random Ka, it has to be the Ka for its conjugate acid. Now that I have Kb, I can calculate pKb, which is the negative log of Kb. Negative log 1.74 times 10 to the negative 5 equals 4.76. So 4.76 is the pKb, when 1.74 times 10 to the negative 5 is the Kb. Both of those numbers are true for NH3. We're now going to work through the calculation of the pH of a weak base. The question that we'll work through, calculate the pH of a 0.1 mole per litre ammonia solution given the Ka of its conjugate acid NH4 plus is 5.75 times 10 to the minus 10. We'll work through the same 5 steps that I used in the weak acid video. The first step is to write an equation showing the substance in water. So there's my NH3 in water acting as a base. It's receiving an H+, it's forming ammonium and hydroxide. It's always a good check to make sure that if you are dealing with a basic solution, it is producing OH- in solution. Now let's do a little bit of thinking. We know our concentration of ammonia is 0.1 mole per litre. So we're starting with 0.1 mole of ammonia there. Just like for our weak acid calculation, we don't know the exact amount of ammonia that's turning into NH4 plus and OH-. But we do know a little bit of it is, or some of it is. So let's say the amount of ammonia that's reacting is X. For every 1 NH3 that receives 1 H plus from 1 H2O, we're going to get 1 NH4 plus forming and 1 OH minus forming. So for every X number, we're going to get X forming and X forming. We are going to get a little bit of extra OH minus produced, again, from the dissociation of water, where H2O plus H2O forms H3O plus and OH minus. That's going to produce a little bit more OH minus, so it's not going to be exactly equal between these two. There'll be a little bit more OH minus. Again, we are going to make two assumptions. Assumption A is that because so little NH3 actually dissociates, we're going to say none of it does. We'll call that assumption A. I've written that here below because so little NH3 dissociates, evidenced by our small Kb, which we'll come across shortly. We will assume that none does. So our concentration of NH3 is 0.1 mole per litre. Our second assumption is that because so little OH minus is contributed by the dissociation of water, we're going to say none of that is as well. So the OH minus ions from the water dissociation, which is Kw, are so few that we can ignore them. So step 1, write our equation, do a bit of thinking about what's going on, and record our assumptions. On to step 2. Step 2 is to write our Kb. So Kb is products over reactants. So just to refresh your memory, our products are NH4 plus and OH minus. Our reactants are NH3 and water. Water we will exclude because its concentration is so high we can assume it to be constant. So there is our Kb expression there. NH4 plus and OH minus over NH3. Step 3 is to substitute in our values. So what values do we have? Well, we've got OH minus, we're going to call it X. We've got NH4 plus, we're going to call it X. We've got NH3, we're going to call it 0.1. We don't have a Kb. What we do have is the Ka for the corresponding weak acid. This is fairly standard for an exam question for calculating the pH of a weak base. They often give you the Ka of the conjugate acid. So our first step is going to be turning that Ka into a Kb. So we're going to rearrange our Ka times Kb equals Kw equation, where Kb will equal Kw divided by Ka. Kw is a constant, it's 1 times 10 to the minus 14. Our Ka was 5.75 times 10 to the minus 10. Divide one by the other, and it gives us our Kb, which is 1.74 times 10 to the minus 5. So now we have a Kb value that we can plug into our Kb expression. So we have that, we have that, we have that, and now we have that. Those two are X, that's 0.1, that's 1.74 times 10 to the minus 5. So let's now substitute those values in. 1.74 times 10 to the minus 5 equals X times X, which we can rearrange to say X squared, divided by 0.1. So here is that rearrangement. To get X on its own, we can square root both sides. And then we can call X what it actually is, which if we go back to our original equation, X is the OH minus concentration. It's also the ammonium concentration, but that's not going to help me get pH. OH minus will. So I'm going to relabel it OH minus and solve it to give me 1.32 times 10 to the minus 3 moles per litre. You've probably identified that we cannot get pH directly from OH minus concentration. We have to first get to the H3O plus concentration. So I can rearrange my Kw expression, which is H3O plus times OH minus equals Kw. That number's a constant, 1 times 10 to the minus 14. So I can rearrange it to find H3O plus like so. I can then substitute in my values. And then reveal my answer as 7.58 times 10 to the minus 12 moles per litre. Now that I have my H3O plus concentration, I can find my pH. Step 5, solve for pH. pH equals the negative log of the hydronium concentration, negative log of that 7.58 times 10 to the minus 12, which equals 11.12, or 11.1 if we round at the third significant figure. So that's the process you can use to calculate the pH of any weak base, assuming you know its concentration and either the Kb of that weak base or the Ka of its conjugate acid. So, your turn. Calculate the pH of 0.05 mole per litre CH3NH2 solution, given the Ka for CH3NH3 plus equals 2.0 times 10 to the minus 11. I know this is a weak base because, one, from our organic unit, we can identify this as an amine, and amines are basic when in water. The other way I can identify it is because this and this look very similar. They differ by 1H+. This ends in NH3+. This ends in NH2. So this is the conjugate acid. This is the conjugate base. If we have the Ka for the conjugate acid, we can find the Kb for the base, and then find the pH of the solution. Pause the video here and do the calculation. I'll reveal the answer in 5 seconds. The answer is 11.7. I hope you found this video helpful. See you in the next one.